Howdy, folks. Welcome to the second installment of Dr. Eigenstate Explains. And in this video, it's going to be a fun one. We are going to be covering an interesting topic indeed called wave function collapse. Now, you will probably remember in the last video, I introduced what a wave function is and introduced three important concepts to it. The normalization condition, that all of the probabilities defined by a wave function for some given state must equal 1, i.e. one of those states must be observed when you actually make a measurement. The Born rule, that the coefficient associated with any of the states squared represents the probability of observing that state, and something that I am going to expand a little on in this video because it's a little more relevant to this video, superposition. And a good friend of mine gave me a really intuitive way of summarizing what superposition is in just a really simple and easy to understand way. So let's take the number 6. How many different ways can we get to 6? Well, we could do 1 plus 1 plus 1 plus 1 plus 1 plus 1. That's one way we could get to 6. We could also go 2 plus 2 plus 2. That's another way we could get to 6. We could go 3 plus 3, or 4 plus 2, or 5 plus 1. Each one of these is a way of getting to 6. You could say 6 is a superposition of each one of these ways of getting to it. Simplistic, intuitive understanding of what superposition is. And before we dive in, I'm going to explain superposition in a little bit more of a specified context that's going to apply more appropriately to what we're talking about. But first, let's get our space that we're going to be working with set up. We have one axis here. One axis here. Oh, that's not what I was trying to do. And we're going to have one axis here. We're going to be working with a three-dimensional coordinate space. So just kind of picture that you're looking sort of into the corner of a room. That kind of gives you an intuitive look that this is three-dimensional coordinate space. But this isn't any old type of space. We're going to be working with something called a vector space. Not really that hard to understand. The first thing I want to state is I want you to think of these as axes in your mind, because that's sort of what they are, in the sense that any position in this space is going to be represented by a certain quantity on this axis, given by a certain quantity on this axis, given by a certain quantity on that axis, to get to that point. So that point is a combination of some quantity along each of the three axes. And that's going to be important. But we're not going to be dealing with axes. We're going to be dealing with basis vectors. Like axes to a point in a traditional coordinate space, where any point in that space is a combination of three quantities, one on the x-axis, one on how far you have to go along the x-axis, how far along you have to go on the y-axis, how far along you have to go on the z-axis. That point is a combination of those three quantities. In a vector space, it's somewhat similar, but there's some differences. A vector that you map in that space is a combination of the three vectors. So you've got, for instance, how many units you're going to be going this way, how many units you're going to be going this way, and how many units you're going to be going this way to get to the point, and then you would have another point at the origin to get to the point out here defining where that vector is. So instead of calling them axes, we would call them basis vectors, because like an axis, any point in a coordinate space can be represented by a number on each of the axes, a combination of numbers along those axes. Well, any vector in a vector space can be represented as a combination of the basis vectors. And this black one that I've drawn here is going to be psi. And that little bracket with the line, the bar with the bracket, just means that it's a vector. That's really all that means. The technical term would be a ket. And since we're mapping the wave function as a vector, it's generally called the state vector. But state vector just refers to the wave function when it's being mapped as a vector in a vector space. So instead of calling this the x-axis, this would be the x-ket, or x-vector, the y-ket, or the y-vector, and the z-ket, or the z-vector. And superposition in this context simply means that this state vector is a combination of three or potentially more, because in the types of vector spaces you use in quantum mechanics, you can have n dimensions. You can have up to infinite number of dimensions. Any vector can be written as a combination of those basis vectors, which is why we call them basis vectors. So any vector is in a superposition of all of the basis vectors that make it up. It could be the x, the y, the z, the b, the c, the a, but it's a combination of all of those. It's in a superposition of all the vectors that form the basis. And the basis of a vector space is just the vectors that which any other vector in that space is a combination of, generally called a linear combination. So that is what superposition means in this particular context. Now you might be wondering, well, what does this have to do with quantum mechanics? So we're going to be dealing with position. Position is an observable in quantum mechanics. Momentum is energy, time, spin. These are states that one can observe a particle in, or a state that a particle is doing. So we call those observables. Observables are represented, before I tell you what observables are represented by, each one of these basis vectors, the x basis vector, the y basis vector, and the z basis vector here represent three different positions that our particle, which is represented here by our state vector, again the wave function mapped as a vector, they represent three different positions that particle that is represented by our state vector could be in. So the state vector is currently in a superposition of those states. It isn't in any one of those states, it's in a combination of those states. For a sort of intuitive understanding of what superposition is here and why it's important. Observables in quantum mechanics are represented on a vector space by something that I'm going to dub O hat. This is called an operator. The operator represents the observable. So for position, which would be x hat, the position operator of, and that was drawn really poorly, I apologize, of the wave function of x is equal to, I believe it's x psi x. Or is it just psi x? It's one of the two. Let me double check. I know what the momentum operator is off the top of my head. I don't know what the position one is. Yes, it is. Yes, I had that right. Oh, if I could draw and not erase, that would be great. Sometimes you gotta double check, make sure you're getting things accurate. Xi x. This would be the position operator. This is what's going to tell us, essentially, what position the wave function is going to take when we decide to actually make a measurement. That operator is, and this is a little bit loose, but it's still accurate for what we're doing here, is essentially going to be what we use to make the measurement. So how do we do that? How do we take this state vector, the wave function, when you map it as a vector, how do we take this state vector, which is currently in a combination of 3 different positions, and figure out which one of those positions it's actually in, or that the particle that it represents is actually in? Well, we take our operator, and our operator, again, in this position, is the position operator that corresponds to, the observable that we're measuring. And it's going to act on the wave function. And what it's going to do, I want to get rid of that. What it's going to do is something interesting called projection. And I'm going to give an intuitive explanation of what projection is. So let's say we have a flashlight here, a little on-off switch, and it's shining light onto this vector. Well, what's going to happen is it's going to cast a shadow onto what would here be the x basis vector. You could intuitively understand it as the x-axis if you want, but it's a vector. It's going to cast a shadow down, and I'm purposely making this nice and thick, down onto that basis vector. Now, you can imagine if you did it the other way, if you took this and put it facing that way, it would project it that way onto the y vector, and you could orient your flashlight and cast a shadow onto that basis vector as well. So what projection is, when you take your operator and you act on your state vector, you will project it down onto some basis vector. It will randomly project the state vector onto one of the basis vectors. And what will happen then is you will get, let me do this in a different color just to make this a little bit, try to make it a little bit more intuitive here. You will get a new vector. But one thing you might be noticing, excuse me, right off the bat here is this new vector right here is not the same length as our x basis vector. That is a problem if you haven't already figured out. Well, there is something that we can do. I'm going to change the color again. Let's go. That'll work. There's something that you can do. You can scale the projected vector, this purple vector here, to match the basis vector. And you're casting the shadow down onto the basis vector and then lengthening that vector to match the length or the magnitude of the basis vector. For those that don't know, I probably should have covered this, but kind of assumed everybody would know, that a vector is an object with a magnitude or a length and a direction. How long the arrow is and in which way the arrow is oriented, which way it's pointing in the vector space. Vectors aren't hard to understand. So what we can do is we can make that vector longer, and the amount by which we made it longer will be represented by a quantity, just a number, and we call that number lambda. That value, that number, has a specific name. Called an eigenvalue. And I will explain why it's called that here in a few minutes. So this new vector that we have, which is the purple vector, the purple vector plus the teal vector, that whole vector combined, I'm going to go back to black since we're talking again about our state vector here, will give you a new vector. Ignore the position that it's in. That's not the direction that it's pointing or its orientation. That's not relevant here. That you will get a new vector that is the purple and the teal vector added together. That is called an eigenvector. An eigenvector is it's a vector, it's a special kind of vector that, I got popcorn sticking in my teeth, it's bothering me when I'm talking, sorry. An eigenvector is just a special kind of vector that changes, technically speaking, changes by a scalar value under transformations. So what that means is one of two things. Either A, the direction that it's pointing stays the same, but it gets longer or shorter. It's generally longer, but it can get longer or shorter. So the magnitude can change, but the direction stays the same. Or the magnitude stays the same, but its direction changes. Only one of the values changes, but not both. A vector that can do that, where only one of its values can change, is called an eigenvector. And the value by which, in this case, the vector got longer is called the eigenvalue. That's the number by which that vector got longer. We call that the eigenvalue. And interestingly enough, the eigenvalue corresponds to the quantity that you measure when you make the measurement. So this lambda is the quantity associated with position. And the position that we've observed was this one right here, because our operator projected it on to our blue basis vector. So that position is what we observed. And the state, the quantum mechanical state, the quantum state associated with, again, this eigenvalue is called an eigenstate. We put eigen on it because it's represented by an eigenvalue or an eigenvector, that vector that changed. And the eigenvalue of the eigenvector, the amount by which that vector got longer, so since it got longer, it's an eigenvector, and the value by which it got longer is the eigenvalue. The eigenstate corresponds to the eigenvalue of the eigenvector. So that eigenstate is the position that you observe that particle to be in. This whole process, I'm going to clear some things up now. This whole process that I've just gone through, that didn't work as well as I thought it was going to, is summarized by a fancy term. If I could get this cleared up. I really wish they could let me make it bigger. I've tried, they won't. It's called state vector reduction. You have reduced that state vector, that vector representing the wave function, from being in a superposition, a combination of three possible states. You have reduced it to only one of those states, and that state was the one that you observed for its position, where it's at. This is more colloquially known as, this is the technical term, this is more colloquially known as, you've probably guessed it by now, wave function collapse. The wave function has collapsed from a superposition of three potentials, in this instance, three potential states, to one of those states. Now, that is the technical, still there was some, hopefully some intuition there. There was a more technical description of what wave function collapse is. Now I want to get my get another coordinate space going here. I'm going to try to make this a little bit more, give a little bit more of an intuitive explanation of what it really is and why we call it collapse. Let's go with a different color here. Let's go with red. Yeah, everybody likes red. It's a little bit longer than what I need it to be. So here we have a coordinate space, and I'm just working with two dimensions here because it's going to be easier for this intuitive description. And in it, we're going to use green. We have some wave function. Let's go with a basic one, an interference pattern. Actually, no, we don't need to. We've got some wave function. The amplitude corresponds to the probability. So obviously, the higher this is, the more probable you have. So this particle is quite likely to be here, but not so likely to be here. it's a little bit likely to be here, same here, but especially here, it's like pretty much you're not going to observe it there. So we would say that the wave function has collapsed when you make a measurement and now you observe it to be in some state. And I'm going to go with blue here, and we're going to draw lines that represent standard deviations here. And this is why you might often see sigma, I hope I drew that the right way, I think I did, being used in quantum mechanics. So you might notice that when we observed the initial wave function, when we made a measurement on it, the one that was in green, we got this yellow one. And you'll notice that the yellow one is in a standard deviation. What this means is that we can confidently say that the particle has disposition x. And what happened here is you can see it's not, the wave function isn't tracking this green anymore. It's tracking the yellow. So you would state that the wave function has collapsed to this position. Somewhat of a more intuitive. It's collapsed to within a standard deviation that allows us to confidently say where the particle is, or what its momentum is, or what the observable is. Wave function collapse. The wave function is gone from, if you can imagine, like a typical bell curve that my hands are making, and then it collapses. So we know that right along in here is where the particle is at now. We can confidently say that is where the particle is at. So that is a little bit more of an intuitive depiction of what wave function collapse is and why it's often called wave function collapse. And just one other thing I want to point out, because it might lead into a third video. It might not be the next video I do, but it might, is, I don't know why I got rid of my axes. I needed those. Oh well. Life's a bitch and then you die. Or you marry one, it just kind of depends. No, is that still at 90? No, not anymore. 90. There we go. Let's get this axis back up. Sweet. Alrighty, let's use blue this time. You may have heard of the double slit experiment. And this is going to lead into another video that like I said, I'm probably going to do. It might be the next one, it might not. I might move off quantum mechanics for a video. The double slit experiment tells us if we take a beam of light and we reduce it to where we're shooting out individual photons, so to speak, we should see them go through one of the slits or the other. Meaning that we should see a bunch of photons either here or here, but that's not what we see. What we see is an interference pattern, something like that. Until we turn on something that detects them, whether it's before or after they go through the slits. Then we get something that looks a little different. A lot of people would state that you've collapsed the wave function of those photons when you measure it. I don't think that that's actually true. What is it? I could be wrong on this. I don't think I am, because I'm rarely wrong. But I think what happens is you've got two slits. The wave function doesn't collapse. It just changes its structure. From an interference pattern, when you're watching them, it goes to looking more something like that, with the two humps corresponding to the slits where you're most likely to find the particles. So the wave function didn't collapse in that instance. It just changed its structure. The structure of the wave function changed. And in the next quantum mechanics video I do will be on wave-particle duality, and I might touch on this a little bit more. After that, I might do time evolution of the wave function via the Schrödinger equation. I'm really not as well versed with the Schrödinger equation as I'd like to be. I mean, I know what it is, I know what it says, I know what it tells us, but in terms of doing a video on it, and I don't know if I'm really comfortable doing that. But the next quantum mechanics video, I can't promise it will be the next video that I do in this series, but the next one that I do on quantum mechanics will be on wave-particle duality. So I'm going to leave you with that for now. And before I go, as always, per causam nos perfectum, or through reason we progress.